Nylon-6 is a polymer that contains sequences of 6 carbon, 1 oxygen and 1 nitrogen. So if we do a measurement, that is to say an XPS measurement from a sample that is supposed to be nylon-6, if we look at a survey spectrum and set up regions for the oxygen, nitrogen and carbon, we ought to end up with background subtracted intensities, which when scaled by the relative sensitivity factors should lead to the ratio of 6 to 1 to 1. Let's examine this using the report spec page, and if we do the ratio of carbon and oxygen to nitrogen, then we can see that the amount of carbon changes in this sequence of measurements. And the difference between these different measurements is that an argon cluster ion source has been used to etch the sample or sputter the sample with the intention of cleaning the sample. And you can see that initially we've got 8.5 for the ratio, 8.6 for the ratio of carbon to nitrogen, and following etching it's getting closer to 6. 6 is what we would expect, so given that these are survey data, we will consider this to be an indication that after one etch cycle we might be getting closer to what the nylon looks like. So let's consider these carbon 1s spectra. And once again, when you measure by XPS a nylon sample and you concentrate on the C1s signal, then you end up with a data envelope that is a combination of chemically shifted C1s peaks. So let's create a background, and we'll now create a peak model that will represent what we believe this to be. I've chosen the second one rather than the first one, so that there was a greater indication that we had nylon following the first etch cycle. So we'll create some synthetic peaks and we will position them roughly where we think these different materials ought to arrive when chemically shifted C1s is considered. So what we've got is, this is going to be a CH peak, and if we just go and have a look at our polymer again, let's see what this looks like. So we've got 3 of them which are bonded to hydrogen and bonded to carbon. We've got 1 that is bonded to nitrogen only, and we've got 1 that is bonded to oxygen, nitrogen, and then 1 that is bonded to the carbon that is also bonded to the double bond to oxygen. So we'll consider these as being 4 different environments for the carbon peak, and hence when we select the carbon 1s data envelope and also the peak model, we are anticipating this one to have 3, and each one of these should be 1 in intensity. So if we say fit, we'll get a fit which we can also use by include the ratio. We can use this to create a report over the data in the annotation, which is based on these components. And if this were nitrogen, we would expect 3 here, so this would be 1, and that would be a third, a third, a third. That would be nylon. However, we don't have nylon just yet, but that doesn't mean to say that we don't have nylon. We may need to introduce some constraints to make this peak model give us a reasonable representation of what we'd expect for nylon. So first of all, what we'll do is we will say that the column B will be C times 1. So that's here. So that one, we'll call that one CN. And this one is going to be CC double bond O. And now we say fit. Well, now we end up with something that's a little closer. These are about a third, and then something that's slightly less. Now, this one is the double bond C double bond O. And I think we did see that even in the survey spectrum that there was slightly less oxygen expected than the nitrogen, and that's indeed what we've come up with here with our peak model. And that's after one etch cycle. So what does it look like when we apply this peak model to the first as received surface? Let's have a look at that now. And now you can see that indeed we have got, in the first one, this peak model is now indicating that you've got two that are the same size. You've got slightly less oxygen, and we've got more carbon than we expect. These should be a 0.33. And let's see what this says. Well, that's interesting, because we've got, from our survey spectrum, it's indicating we've got less nitrogen and more carbon and more oxygen. So our peak model clearly isn't reflecting what the survey spectrum is indicating. So that shows us that we really have to consider very carefully what a peak model is trying to tell us. Simply because we introduce a constraint and we get an answer in one case, such as this one, that makes some sense, the same didn't apply for the as received surface. When this peak model was constructed, there was a preconceived idea that we had nylon. So the peaks that were introduced, the number of peaks and the ratio of these peaks have been entered into a peak model so that we are testing the data against the possibility of seeing nylon. And we can see that in the first instance, when the as received data, it wasn't quite nylon, so the model is perhaps imperfect. So rather than having a preconceived model, let's go with a new approach that relies on extracting the information from the data rather than imposing what we think it might be there. And we're going to use an option on the test data tab to merge these oxygen, nitrogen and carbon peaks so that we have data that represent the as received, that's the first one, and the second one is after one etch cycle. And you can already see that there has been some alteration of the material. Just simply by looking at the intensities here, you can see that there's more oxygen and less carbon the moment the ion beam has touched the sample. So we're going to use an option on the calculator where we can calculate a sequence of different spectra. In this instance, we've got two spectra that are very similar in intensity but slightly different, and so we don't have to do any pre-processing of these data to do this calculation. We'll just take the difference of these two sets of data, and having taken the difference, the idea is that we start off with the two forms as the first and the last in this list. So when we overlay these are exactly what we saw before, and then somewhere in the middle what we will find are spectra that have different characteristics from the ones that we measured. So these are going to be synthetic spectra, but we're looking for characteristics of the initial state where we think we've got nylon, and some form that would represent what has been removed by the sputtering process. Now we can see here we've got peak, but it's starting to cause a negative going peak here, so we won't allow any non-physical type peaks in these two spectra that we're going to look at. We've got here, that looks reasonably good, and we've got an oxygen peak, and this oxygen peak is interesting because the background is flat here, and I'll show you why that's significant when I come to the next spectrum that I'm going to identify. So we've got a CH type peak. That looks like something that is an oxygen bonded carbon peak, and there may be a shoulder here representing the nitrogen. So overall this looks like a physically meaningful type of spectrum. So we'll take a copy of that one, and having arrived at that point in this sequence, what we'll do is return to that point here and start searching again. And the idea is that we find two different spectral forms. Both need to look physically meaningful. So when I arrive here and I see a sharp drop here, or a deep valley here with some not as meaningful as I would like to see in terms of what I'm expecting from these data, I will carry on going, and that's what the carbon looks like. And we'll look at the others. So we've still got something happening over here. Now I'm going to focus on the oxygen, because what I'm expecting to see, if this is going to be a polymer like nylon, I am expecting to see a band gap, and in this oxygen I can see a flat portion here of the spectrum with a step that is associated with the onset of possible energy loss events associated with this oxygen peak. So that's a plausible type of background associated with this oxygen peak. The peak itself looks reasonably well formed. What do the other peaks look like? That's a reasonable nitrogen peak. And let's see here, we have a plausible carbon peak. So let's take a copy of these. And this is an iterative process that you may not choose the best two spectral shapes. So this is one of many applications of this approach, so that we can have a look and see what's happening within these data. So essentially what we've got here are two different forms of the carbon 1s. It's not so obvious, there are two different forms here for the nitrogen, but it is more obvious in the oxygen. You can see that the oxygen is shifted in binding energy, the background is flat, so we've got two different shapes that may have some physical significance to these data. So what we'll do next is go back to the set of merged oxygen, nitrogen and carbon, and we'll copy these two calculated spectra and overlay them in the active tile. Select the entire set of data that we constructed from the oxygen, nitrogen and carbon, and then using an option on the PCA property page we'll generate spectra. And what this will do is create an approximation to each one of these spectra using the two calculated vectors or spectra. So this is one, this is the other that I calculated, and these have been scaled according to least squares solution, so that when I combine this row as an overlay, you can see that we reproduce almost exactly, well, within numerical error, the first two spectra. So you can see there that I've now got two different proportions of these two spectral forms, both of which reproduce, because this is not just red, there's also a green spectrum here. If I offset them, you can see they're actually red-green. These are so close in terms of precision, numerical precision, that the sum of these two spectra produce this green one, and the red one is overlaid almost perfectly. So let's put that back to, so you can't see them. And now we'll apply the same basis functions to the other data, and now you can start to see that there is some imperfection here, and that's not surprising. In fact, the surprising thing that it is really as good as it is. So that's fairly good, but what we need to do is have a look at the other peaks, and you can see that there's a mismatch here in the oxygen, and there is a bit of mismatch in the nitrogen, but not too much. So let's try and rectify that by calculating from the raw data in the end of this etch sequence and the calculated spectrum from the least squares solution. We'll try and calculate what was the difference there, so that we can add that back in and get a further insight into what these data, how these data evolve as the etch cycle goes. So let us zoom in so we can see more clearly the carbon, and then I'm going to step through again and we're going to look and see what kind of shapes emerge from this difference. So I'll just rescale. And we're ending up with something that looks fine in terms of the carbon. Let's have a look at what the other peaks look like. That's a nitrogen peak. Let's have a look at the oxygen. There's another oxygen peak. So let's take that one through, and we go to the merged data set. Copying that one. So I've overlaid the 3 different shapes that I've calculated, and once again we go to the PCA property page. I'll select the set of merged spectra that represent the original data, and we'll generate using 3 components, and this time we'll have a look and see what happens. So as before, you can see the first one has a certain characteristic shape, and when I go to the second one, the proportions of those 2 shapes change. So the idea would be that this one here would represent the nitrogen, and this one represents what has changed as a result of etching the sample. And then as we carry on etching, you can see that this is well represented by these 3 component peaks, and what happens is you end up with an evolution of that one that I just calculated from the least squares solution for the last vector. So we can see that there is some trend here that makes some sense. We're continuing to etch the nylon and sputter, and the changes to the material as measured by XPS can be monitored by this peak that evolves. It would be reasonable to ask the question, is XPS capable of understanding stoichiometry to the precision required here for nylon, where we're expecting 6 carbon, 1 oxygen, 1 nitrogen? And the answer is, in this particular case, yes. And the reason is that I've used Schofield cross sections that have been corrected for escape depth. So the kinetic energy of the different electrons here from the nitrogen, carbon and oxygen, they all come from a slightly different depth, so you have to make a small adjustment for that, for the escape depth. The other side to this is that these are very close, so that adjustment is relatively small. When I say close, they're close in kinetic energy, so they're all sampling close to the same depth. And the next statement is actually about the instrument itself. And this is an imaging instrument, and it has the advantage of, although we're measuring spectra using the spectroscopic mode through the deflection hemispherical analyzer, we can image the slit, or rather slot aperture, that is used to collect these spectra. And this is at a binding energy of 85 electron volts. And if I slide up this binding energy scale or down in kinetic energy, you can see that an image remains part of the analysis area in this particular mode. We're using field of view 1 slot mode to measure these spectra. And because these images are very much there and relatively stable here, although you can see a little bit of movement, if we look at an overlay of images taken from the different energies associated with the oxygen, the nitrogen and the carbon, when we overlay them, you can see that not only do these images register reasonably well, the size of the image is stable, and more importantly, the intensity across the slot that is acquiring the data in this deflection mode is also stable. So we would expect to see a very stable transmission as a consequence. And we can look at this again using another imaging instrument. This is a slightly different one. And this one has what is referred to as a hybrid mode. And in hybrid mode, the intensity has been set up not for imaging, it's been set up for spectroscopy counts. So I've got two imaging modes, and these all three have been used to measure a silver spectrum. And when I overlay these, you can see that, well, the spectroscopy mode, the hybrid mode, has many more counts than the imaging modes. However, if I take an imaging mode and I then use the calculator and I take the spectrum and I divide the other two spectra by this field of view 1 and display what results, you can see that the hybrid mode has a typical shape that you would see for an acquisition from an instrument that has not been set up for imaging. However, the second imaging mode, when divided by the first, is remarkably similar. They're almost identical. So the response for both of these imaging modes is uniform. So when these data that were acquired on an axis nova from this nylon sample, we can say that we've got a nice behaved transmission characteristic, which you don't necessarily get if you haven't set up an instrument for imaging. And the idea is using the imaging to set up the instrument so that you can get quantifiable spectra through the deflection analyzer.